In this video, we're going to talk about linear programming, which actually is just basically what we've been doing in the last video, so finding a feasible set for a bunch of inequalities with one extra step added to it. So a linear program, or a linear programming problem, is used to help manage decision making. Okay, so it involves optimizing, so that's minimizing or maximizing, some quantity subject to a variety of constraints. So there's a bunch of things constraining the values for x and y, and then you want to optimize some function that we call the objective function. Okay, so it's going to be and it has to be in terms of x and y. The constraints are going to be inequalities that affect x and y. So they restrict the values of x and y. So what we're looking for when we want to optimize the objective function is we want the feasible set for these system of constraints. So those are all the possible values of x and y that satisfy all the constraints. And then we want to find the exact point that gives us our optimal solution. So this is going to give us the biggest or the smallest value of z depending on how we're trying to optimize. So this is probably going to be more clear with an example. So we start with one in where we have to construct the linear programming problem. So suppose there's a new brewery in town and they want to make two new types of beers. So they want to make an ale and a porter. Each keg of ale requires 8 pounds of malt and 6 ounces of hops. The kegs of porter require 10 pounds of malt, 5 ounces of hops. And the keg of ale profits $40, whereas the keg of porter profits $45. Now, they have restrictions on the amount of malt and hops that they have for the week. So they have 100 pounds of malt and 60 ounces of hops available. And they want to know how many kegs of each should they make in order to maximize their profits. So let's try to summarize this. So first of all, our objective function is going to be that we want to maximize the profit. Okay, so the way that we find the objective function is because it says it's the thing we want to maximize or minimize. So here we wanted to maximize the profit. Okay, so that's our objective function. Now, let's just say, okay, I'm going to try and make a little table here. So we have some number of malt, some amount of malt. We have some hops. Okay, and then we have a profit number. Okay, now for ale, for porter, okay, and then some totals. So we know the total for hops is 100 pounds. The total for hops is 60 ounces. And the total profit, this is what we want to maximize. Okay, so for each keg of ale and each keg of porter. So each keg of ale requires 8 pounds of malt and 6 ounces of hops and profits $40. Okay, each keg of porter requires 10 pounds of malt, 5 ounces of hops, and profits $45. So, what we want to know is how many kegs of each should we make. So that tells us what our variables should be. Okay, so let's let x be the number of kegs of ale, and y can be the number of kegs of porter that we make. So then our table, you can see, gives us some equations. So for each keg of ale, we need 8 pounds. For each keg of porter, we need 10 pounds of malt, but we only have 100 pounds. Okay, so this row of our table is going to give us an equation. So 8 times the number of kegs of ale that we make, plus 10 times the number of kegs of porter that we make, should be less than or equal to the total number of malt. Okay, so that comes from that row there. Now the hops has something similar happening. So we have 6x plus 5y should be at most 60. Okay, so again, 6x is the the amount of ounces of hops that we need to make the ale. 5y is the amount of hops that we need to make the porter. So when we add these up, we cannot be more than 60 ounces because that's all we have available. Okay, and then our objective function is going to be the profit. So let's call it P. And for each keg of ale, we're going to make $40. So we're going to profit 40x for ale, and 45y for the porter. Okay, so then our linear programming problem, what we want to do is to maximize P, our profit, which is 40x plus 45y, subject to these constraints. So we need 8x plus 10y to be at least, or at most 100, 6x plus 5y to be at most 60, and we actually have a couple of other inequalities or constraints as well. So because our variables are the number of kegs of ale and number of kegs of porter, we can't have negative numbers. So the number of kegs has to be at least 0 for each. So we have these extra conditions here. So these are for no negative quantities. Okay, this often occurs in these word problems, so you want to watch for that. So now we just want to solve this system. So what we want to do first is to find the feasible set for this system of linear inequalities. Okay, so the first thing we want to do is find our solution set, or our feasible set. So I'm going to start with the easy ones. Okay, so x equals 0 is the y-axis, y equals 0 is the x-axis, and we want to be bigger than 0 and for both. So that gets rid of everything to the left of the y-axis and under the x-axis. So you don't have to worry about those. Oops. Okay. Now, our first equation here, let's do 8x plus 10y equals 100. So when x is 0, y, or maybe I should say 10y, is going to be 100, which means that y is going to be 10. So I get a point at 0, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I get a point here. Okay. When y is 0, we get 8x equals 100, which means that x is 100 over 8, which we should calculate is 12.5. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half is right here. Okay, so I want to connect those. Okay, so this is our equation, 8x plus 10y equals 100. So we want to test our point. I'm going to do 0, 0 again. So 8 times 0 plus 10 times 0 should be less than or equal to 100. Okay, this is 0 less than or equal to 100. Okay, that's true. So that's on the solution side. So I want to get rid of everything above this line. Okay, so those are not going to be in our feasible set. Okay. Now, no, not red. Let's do orange, maybe. So now I want to do line 2, which is 6x plus 5y equals 60. Okay, so x equals 0 means 5, y equals 60, which means y is equal to 12. So we get a point at 0, 12. Okay, when y is 0, we get 6x equals to 60, so that's x equals 10. So that's a point here. And when I connect those, I get a line like this. So this is 10, 0. So that's 6x plus 5y equals 60. And again, I'm going to test 0, 0. And I get 6 times 0 plus 5 times 0 less than or equal to 100. Okay, that's also true. So 0, 0 is on the right side. So I want to also shade everything above this line. Okay, so our feasible set is bounded. Okay, it has a corner point here at 0, 0. Let's call that A. Corner point here at 10, 0. Okay, that's B. Corner point here at C, which is actually 0, 10. So we already know all of these. And then there's going to be one more corner point at D, which we don't know. Okay, so we want to find corner point D. So it's going to be the solution of 8x plus 10y equals 100, and 6x plus 5y equals 60. Okay, so I'm going to take this one. Maybe we'll solve for y. So 5y is going to be 60 minus 6x, which means that y is 12 minus 6 over 5x. And then if I plug that into the other, I have 8x plus 10 times 12 minus 6 over 5x should be 100. So that's 8x plus 120 minus 12x should be 100. Okay, so subtract 120 on both sides to get rid of that. I'm going to have minus 4x equals minus 20. So x is going to be 5, which means that y should be 12 minus 6 over 5 times 5. So 12 minus 6, which is 6. So the coordinates of corner point D are going to be 5, 6. 2, 3, 4, 5. Okay, which is kind of close to where our point actually is. Okay, so that's probably because of my bad line drawing skills. So we're not far enough away that we get worried about that. Okay, so that is our, so in here is our feasible set. Okay, so any possible solution has to be in this region here. Okay, so that we satisfy all the inequalities at the same time. Now, what we want to do is figure out what point in this region gives us the maximum profit. Okay, so what we're going to do to try and convince you of what's going on here, I want a color I haven't used, so let's try the yellow. So if I, oh, maybe it's not dark enough. Maybe let's use gray. That's different. So if we think about our profit, so P is 40x plus 45y. If I rearrange this and solve for y, I'm going to get y equals minus 40 over 45, which is 8 over 9x, plus P over 45. Okay, so I don't know what P is, okay, but when P is 0, I get a line that goes through point A here, and it has slope negative 8 over 9. So it's something like, it's just under 1. Okay, so it's going to look something like this. Okay, now this is for P equals 0. If P is 45, I'm using multiples of 45 just so that y-intercept is an integer. If P is 45, I'm going to be at 1, but I'm going to have the exact same slope. Okay, P equals 90. I just keep moving up. So what I want to look for, so we want the biggest P so that the line intersects the feasible set. Okay, now if you keep drawing these, I'm going to draw some up here. So it's going to look something like that. Okay, so this is some P. We're getting bigger and bigger and bigger. At some point, we're going to fall out of the region, right? So we keep getting bigger, and at some point, we're going to fall out. Now, what you kind of want to see here is that the last place that we intersect is going to be at a corner point. Okay, so there's going to be a point here. And I think that the slope is a little bit steeper than this line, but it's really close to that line. And then if we're a little bit higher, okay, we might intersect again at this point D. But at some point we're going to fall out. There's going to be a p-value where we don't intersect anymore. So what we want is the highest p that we still intersect with. So what's going to happen is that the maximum occurs at one or more corner points. Okay, now these lines with the p-values change, just so you are aware, these are called isoprofit lines. Okay, so in case you see that word somewhere, that's what they're talking about. In this class, we usually don't need to use them so much, just to sort of convince you that there will be a maximum, and it's going to be at a corner point. So all we need to do is check the corner points. Okay, so I'm going to do that in a table. So I want each corner point okay, and then I'm going to find its p-value. And I want to pick the biggest one. Okay, so A was 0, 0, B was 10, 0, C was 0, 10, and D was 5, 6. Okay, so when we have point A, okay, they're plugging in zeros everywhere. P is going to be 0. For point B, I plug in 10 for X and 0 for Y, so that one's going to be 400. Here I do the opposite. Okay, so 0 for X, 10 for Y, so that's going to be 450. And then the last one, I do 5 for X plus 6 for Y. Okay, and if you do that, I think you get 200 plus 270, so we get 470. Okay, so this is the biggest value. Okay, Okay, so it's the biggest value of P, which means that it's going to be the maximum profit. Okay, this is going to be the last place that we intersect the feasible region. Okay, so now we want to answer the question. So it asks, how many kegs of each should they make in order to maximize profit? So they should make 5 kegs of ale and 6 kegs of porter to maximize profit. And we actually know the maximum profit, so maximize profit, oops, I should say at P equals $470. So what I tried to show for you with the ISO profit lines is the idea of this theorem here, which is called the fundamental theorem of linear programming. So the optimal value, so the maximum or the minimum of the objective function is achieved at one or more of the vertices of the feasible region. Now I should say this is assuming the optimal value exists. Okay, which I'll talk about a little bit, but in our course they will exist. We're not going to ask you for ones that do not exist. Okay, so the procedure to solve these problems is if you have a word problem, okay, you might need to introduce variables, and you're definitely going to make sure you need to know what you need to optimize. So this is to determine your objective function. Okay. Oh, I guess I wrote that down there. But so you need a quantity to be optimized. So this, I shouldn't say determine your objective function. It's the variable of your objective function. So what you want to optimize. And then you want an equation for that and equations for the constraints in terms of the variables. And for word problems, you want to remember often you need no negative quantities. Okay, so these are ones that they sometimes don't say but are implied. Okay, and then we want to graph the feasible set. So that's just like what we did with systems of inequalities. And then assuming the solution exists, we're going to make a table like we just did and evaluate the objective function at each of the vertices to find the maximum. Okay, so let's do an example. So consider the linear programming problem that we want to minimize, okay, this function here. Okay, so this is our objective function. Okay, subject to all these inequalities. Okay, so these are the constraints. So again, I'm going to start with the bottom two. So when y is 0, okay, that is the x-axis. When x is 0, okay, that is the y-axis. And we want them to be bigger than 0. Okay, so that means that everything to the left is gone and everything to the bottom is gone. Okay, oops. Number 3. So we have 2x plus 5y equals 36. So when x is 0, I have 5y equals 36, which means y is 36 over 5. Which is 7.2. Okay, so we get a point at 0, 7.2. 1, 2, 3, 4, 5, 6. So there's 7, so a little bit bigger than 7. Okay, when y is 0, we get 2x equals 36, which means that x is 18. Okay. So that's here. So this is the point 18, 0. and then we connect those to make our line. Okay, remember to label your line. Okay, and then we want to test a point. So I'm going to test 0, 0. So 2 times 0 plus 5 times 0 bigger than 36. So that says 0 is bigger than 36. Okay, that's not right. So that means that we want to shade the side that includes 0, because that is the side that does not have the solutions. Okay, so that's gone. Okay, now I guess we'll use blue for the last one. Okay, so it's 2x plus y equals 20. So x equals 0 means that y is 20, which I think is right up here. Okay, when y is 0, we have 2x is equal to 20, which means x is 10, which I think is right here. Okay, so we connect these. Okay, a line like this, sort of. So that's 2x plus y equals 20. Now I want to test a point. I can test 0, 0 here because it's not on the line. So that's going to be 2 times 0 plus 0 less than or equal to 20. So 0 is less than or equal to 20. So it's on the right side. Oops. Okay, which means that I want to get rid of everything to the right of this line. So all of that's gone. So I end up with this feasible set here. Okay, which has 3 corner points. So let's call that A, let's call that B, and this one here is C. Okay, so we need to find C. We already know A and B. Okay, so let's make our table here. Okay, so we have our corner points and then our objective function. So A is 0 and 36 over 5, or 7.2. Okay, B is 0 and 20. And C we don't know yet. Okay, so we want to find C. So we want the intersection of the green and the blue. So I'm going to use the blue. 2x plus y equals 20. So that means y is negative 2x plus 20. So now I can plug that into the green one. So 2x plus 5 times negative 2x plus 20 should equal 36. So I have 2x minus 10x plus 100 equals 36. So this is negative 8x equals 36 minus 100, which is negative 64. So x is negative 64 divided by negative 8, okay, which is just 8. And then I plug that back into y. So it's negative 2 times 8 plus 20. So that's going to be negative 16 plus 20 is 4. So I get the coordinates here is 8, 4, which let's see if that makes sense. 1, 2, 3, 4, 5, 6, 7. So here's 8. And here is 4. So it's actually really close here. Okay, so we think that we're probably right. And then on this side, we want our objective function. Okay, so that is the thing we haven't even looked at yet. So z is equal to 3x plus y. So when I plug each of these in, so for the first one, I have 3 times 0 plus 36 over 5. So that's going to be 36 over 5, which we already said was 7.2. When I plug in b, I get 3 times 0 plus 20. So that's going to be 20. And when I plug in c, I have 3 times 8 plus 4. So that's 24. 3 times 8 is 24, plus 4 is 28. So we wanted to minimize z. So the smallest z, minimum z, is z equals 36 over 5, or 7.2, which occurs when x is 0 and y is 7.2. So that would be our final answer. Okay, so that's the smallest z we can have, where we would still, the isoprofit line would still intersect this feasible region. Okay, and then any smaller and we're going to fall out. Okay, so it intersects at this point here. That's the last point until you fall out. Now, does this system also have a maximum? It turns out that it does. Okay, and we've actually already done all of the work because we have this table. Okay, so maximum z is 28 when x is 8 and y is 4. Okay, now I'm just going to write a note here. Bounded feasible sets always have both max and min values, solutions. Okay, so because this feasible set is bounded, okay, as our z gets bigger, so let's say our isoprofit lines maybe look like this, as they get bigger, okay, they're eventually going to fall out. And it actually turns out that they fall out here. But so because they're bounded, they have to fall out on both sides, essentially. Okay, so we always have a maximum min when they're bounded. Okay, one more example. So I'm going to do the bottom three like I always do. Okay, so just focus on the constraints first. So this is x equals 0. Okay, this one is y equals 0. And y equals 20 is actually at the top here. Okay, so then we want to the right of x equals 0, above y equals 0, and below y equals 20. Okay, so we're down to this. Okay, now let's do this one here. So 2x plus 4y equals 32. X equals 0 means 4y equals 32, which means y equals 8. Okay, so we get a point here. And when y equals 0, we get 2x equals 32, which means that x is 16. So there's 16. Okay, so we draw that line. Okay, again, I'm going to test 0, 0. So it's going to be 2 times 0 plus 4 times 0 bigger than or equal to 32. Okay, that's wrong. So I want to shade the side that has 0, 0. Okay, so all of this is gone. Okay, now I want to do the other one. So 6x plus 2y equals 36. X equals 0 means 2y equals 36, which is y is 18. So I get a point up there. Y equals 0 means 6x equals 36, which means x is 6. So I get a point down here. Okay, connect those points. And you get a line like this. So this is 6x plus 2y equals 36. And then we're going to test, I can test 0, 0 because it's not on the line. So 6 times 0 plus 2 times 0 is bigger than or equal to 36. Okay, that's 0 is bigger than 36. Definitely not. So I want to shade the side that has 0, 0. So all of this is gone. Okay, which means that all of this is my feasible set. Okay, so notice that it is unbounded. And we have 4 corner points. Okay, so up here, this is going to be 0, 20. So let's call that A. This is another corner point. Okay, so this can be B, and it's 0, 18. We have this corner point down here, so let's call that C. And this was 16, 0. And then we have this corner point D that we need to find. Okay, it's the intersection of the blue and the green. So let's find D. So I'm going to take, let's say, the green one. Okay, so 2y is negative 6x plus 36, which means that y is negative 3x plus 18. Plug it into the blue equation. So plug into blue. I get 2x plus 4 times y. So 4 times negative 3x plus 18 should be 32. So that means 2x minus 12x plus 4 times 18, which is 72, equals 32. So that's negative 10x equals 32 minus 72, which is minus 40. Okay, so we get x equals 4. Plug that into here, means that y is negative 12 plus 18, so y is 6. So the coordinates for D should be 4, 6. 4, 1, 2, 3, 4, 5, 6. Okay, so again, that's actually really close. Okay, good. So when they're unbounded, it means that we may not have a solution. Okay, but for here we do, because we want to minimize this function. Okay, so if we change the black, so if we rewrote this, it's going to be y equals negative 1/2 x plus z over 20. Okay, so as z changes, the negative 1/2, the slope looks like this. Okay, so these are going to be what our isoprofit lines look like. So this is z equals 0. Okay, z equals 20 is going to be like this. Okay, and see, we're not intersecting yet. So as we move up, there's going to be a smallest z for where we intersect. So we can already sort of tell that our minimum should be probably here or here, the corner points that we first intersect. So to figure this out, let's make our table. So we have our corner point, and we have our z, which is 10x plus 20y. Okay, so corner point A was 0, 20. Okay, so that's going to give z equals 400. Corner point B was 0, 18. So that's going to give the z value of 20 times 18, which is 360. Corner point C is 16, 0. So here z is going to be 160. And corner point D is 4, 6. So our z is going to be 40 plus 120. So that's also 160. So notice that our minimum z occurs in 2 corner points. So remember, the theorem said it could happen in 2 corner points. So what that means is that our z value actually has the same slope as the blue line here. So for some z, we actually go through this point, and our isoprofit line is actually this line. So that's the smallest z that intersects, and it intersects along this whole part. So any point along this part of the blue line is going to be a solution. So the way that we write our solution would be the minimum Z is 160 and occurs for any x value with x between 4 and 16. Okay, so those are the x values of C and D. And they have to be on the blue line, and the blue line satisfies the equation 2x plus 4y equals 32. And we have 2x plus 4y equals 32. Okay, so we have infinitely many places where the minimum value occurs. Now my note here is just to say this example has no maximum Z value. Okay, since as Z increases, okay, the isoprofit lines will continue to intersect the feasible region. Or the feasible set. Okay, so just to show you, if I keep getting bigger and bigger, I'm just going to do it with not with a pen. Okay, so these keep getting bigger and they're following the same slope. Okay, they're always going to intersect because our feasible region is infinite, so it's unbounded in this direction. So as I keep getting bigger and bigger, I'm always going to intersect somewhere over here. Okay, so this actually has no maximum. So that's an example where there's no maximum, although in our course we will ask for places that exist. But I just want to show you that there